Now we will see some important and fundamental theorems related to group theory. Okay, so before going to that, I would like to talk about this operator once, A star. So what is this star formally? So mathematically I can define star as a function. So that is going to take a domain as A cross A and codomain as A. And you know what is function, right? In a function, every element is mapped to exactly one element. You know that. So here also star is a function. I can write star like this. Okay. Now, sir, please show with one example. Example, your elements are 1, 2, 3, 4. Then 1 comma 2 might be mapped to 3. This is an example of functionality. So you know one thing, in function, every element of the domain will be mapped, right? That means you have to cover 1, 2, 1, 3, 1, 4. For every combination, you should tell the mapping. And this should not happen, 1, comma 2. 1, comma 4 should not be mapped to 1, comma 2. So because in a function, each element should have only one image. That's why. So from now onwards, you remember when you apply A star B between any two elements. So rather than writing 1, comma 4, I am writing 1 star 4. So 1 star 4 is only single element, okay, and always a single element. Sometimes you might have this doubt, sir, 1 star 3 is, would it be empty at any time? No, because whenever an operator is a function, then every element of the domain should be mapped to something, but exactly one element. That's why. So from now onwards, when you have two elements, always A star B is a single element, remember. Let's talk about the first theorem, left cancellation holds good. In a group, why left cancellation holds good, we will see. So that is nothing but A star B equal to A star C, then B equal to C. Why we can write it? We'll see that. A star B equal to A star C. Whenever this happens, then I can cancel A and A. Here, don't say that, sir, it's obvious. Always we can cancel like this. No. Maybe in multiplication in your calculations you might have done. It doesn't mean that always it holds good. Okay, that's wrong. So that's why don't take it as granted. But we are going to prove that if you take any group, in that group, so A star B equal to A star C. That's the beauty of this abstract algebra. So we don't know what is that star, right? What is that operator? How it is mapping elements to elements, correct? But still we are talking about some of the properties of all such operators. That's the beauty. Now we'll see why A star B equal to A star C, then B equal to C. Let me prove it. For that I take inverse. So let me take A inverse, which is this one, star A star B equal to A inverse star A star C. Sir, how can you say that this is correct? Simple. I have taken A star B and A star C. Both are same means it's a single element. A star B is one element, correct? You can say X. If A star B equal to A star C, then this also should be X. No, there is no other option, correct? Now, and one more thing, you know that A star B is a single element. If this is X, then here also it should be X. Fine. For X, we are applying, this is X, this is X. So for X, we are applying A inverse here, A inverse here. So again, same story. A inverse star X is a single element. Then here also it should be single element. Finally, so we did what? A inverse star A star B. Here also A inverse star A star C, both should be equal, correct, according to the operator's property. Now, but A inverse star A is what? E, correct. So that's why E star B equal to A inverse star A, E star C, correct. But E star B, because E is identity element, correct, identity star B is B equal to E star C, C. So that's why B equal to C. Sir, here why you are stressing that, A inverse star A star B equal to A inverse star A star C? It looks obvious, no. Example, that star is not a function, then what can happen is maybe A inverse here. Example, A inverse, you have already X equal to X. Okay. Now, whenever X equal to X, then A inverse star X equal to A inverse star X may not be true always. Sir, in which case this cannot happen? If when you apply this operator star, A inverse star X gives two elements. One is Y. I am assuming that A inverse star X gives multiple elements. One is Y1, second one Y2. Then A inverse star X if you take Y1 here, A inverse star X if you take Y2, Y1 equal to Y2, ultimately wrong. That will happen if that star is not function. But we know that star is function. That's why I was stressing that point. So There is no such problem here. So finally, left cancellation holds good, right cancellation holds good. Now we'll see third one, exactly one identity element. So as a discrete math faculty, whenever there is some statement that has to be proved, then what I do is I go for proof by contradiction. So here I assume that there are multiple identity elements. First let me take E1 as an identity element. What is the property of any identity element? That's fine. Always hit the root. What is the fundamental definition of any identity element? If E1 is an identity element, then E1 star A, let me write here, E1 star A equal to A star E1 equal to A, correct? Remember it. Let me use that. That means E1 star anything, right? So in the place of A, let me take E2 because it should hold good for anything. So E1 star E2 equal to E2 star E1 equal to that other element which is E2. Second, because E2 is also identity element, let me use that result. E2 star E1 equal to E1 star E2. Here E2 is an identity element. Of course E1 also, but at this moment let me assume E2's property. So now see, these two statements are correct. Now there is a contradiction. E1 star E2 we have here, let me take. So E1 star E2 is E2 here. Same E1 star E2 here is E1, correct? But you know one thing, this operator is a function, so this E1 star E2 is a single element. So then why you got two elements? So here also it should be single element. That's why E1 equal to E2, there is no other way. So finally, every group has exactly one identity element. Now we'll go for fourth one. For every element, there exactly one inverse. So this statement says that you take any element in the group, exactly one inverse will exist. But why? What is the reason? We'll see. Again, proof by contradiction. So there is an element A. Let's say it has two inverses. That is, one is B, second one C. Okay. Let us target B. Really B is an inverse of A. What is the rule? A star B equal to, that's why we are just hitting the fundamentals. B star A equal to E. Remember it. Statement 1. Now, second thing, C is also inverse, right? What I do is I apply, see, just learn with my experience. With my experience, I am proving this one. You just understand how I am proving. Okay. So next time when a new problem comes, this experience helps you. Okay. Now A star B equal to B star A equal to E, correct, right? Let me apply C at left side. What happens? We'll see. C star A star B equal to C star B star A, otherwise A star B equal to E, right? So C star A star B equal to C star E, correct? Fine. But C star A, C is inverse of A, right? Then C star A equal to E. So E star B equal to C star E. But you know identity element property. So C star E is C. But E star B identity element E, correct? E star B equal to B. So B equal to C. That's it. We proved it. That means initially we assumed element A has multiple inverses. Whenever there are multiple inverses, they are becoming same. That's why remember, for every element in the group there is exactly one inverse. Whenever I took two, I am contradicting myself, right? Now the fifth one, A inverse whole inverse equal to A. That means A inverse is, you know, that inverse of A, right? Its inverse again A. That's obvious, but we prove it. So the question, A inverse is one element, don't worry about it, forget about that. It is the inverse of A, okay? Whose inverse is A inverse? A's inverse, remember. So A inverse whole inverse equal to A. Why, sir? Simple. A inverse has an inverse called X. We have to find out X value, correct? Okay. But what is the property of any element's inverse? If A inverse has X as inverse, A inverse star X equal to X star A inverse equal to E. We know that. That's why again we are hitting fundamentals. Now A inverse star X, correct? So let me apply A over left side, because always, you know, if I apply A star A inverse, I get fun because I get identity element, then probably some simplification will happen and we get result. That's a experience. So what I am going to do is I am taking this result, I am applying A star over left, A star A inverse star X. That means I am applying star between A and this A inverse star X, but we know that that is equal to A star E, correct? Because we have E here, forget about this one. Now A star A inverse E E star x equal to A star E. A star E is A. So E star x equal to E. So E equal to A. Correct? Sorry, E star x is x, right? So x equal to A. Right. But what is x? Our initial claim is x is A inverse inverse. So that's why A inverse inverse, which is x, equal to A. That's why A inverse whole inverse equal to A. It's easy. Correct? Now we have proved some of the fundamental results, but we will take some more results and we try to prove. Okay. Now we will see two more results. One is A star A equal to A, then why A equal to E. Okay, that is one thing. Second thing, A star B whole inverse equal to B inverse star A inverse. We'll see one by one. So remember, we have group already. So in a group G star, the first statement is A star A equal to A, then we have to prove that A equal to E. So what I do is, I do cancellation because I know that left cancellation holds good, right? So I write like this, A star A equal to A star E, correct? Because A star E is nothing but A. Now apply left cancellation, then A equal to E. So from now onwards, you remember, whenever you apply A star, that means for any element A, star A, that same element, then if you get same element back, that means that must be identity element. That's it. Now the second one, A star B whole inverse equal to B inverse star A inverse. Why it is true, we'll see. So let us begin with A star B. Assume that A star B inverse is x. Okay, then what happens? A star B, I am assuming that A star B is inverse equal to x. Then A star B star x equal to E. That is the first step, right? So what I am going to do is, I am going to find out x value, correct? So first apply, the trick is very simple. I want to cancel this A, I want to cancel this B. For that I apply A inverse over this equation. So A inverse star B star x equal to A inverse star E, correct? Yes. We know that A inverse star A is E. So E star B star x equal to A inverse star E equal to A inverse, we know. E star B equal to B. So B star x equal to A inverse, correct? Now let's cancel B. For that apply B inverse over that equation. B inverse star B star x equal to B inverse star A inverse. So B inverse star B E, correct? E star x equal to B inverse star A inverse. So E star x equal to x. So finally x equal to B inverse star A inverse. Now recall, we thought A star B inverse is x, right? So that means we assume that x equal to A star B is inverse. So we can say that A star B is inverse. So that's why A star B inverse is B inverse star A inverse. In that way easily we can understand it. Now we'll see one more concept, that is abelian group. What is abelian group? Abelian group is a group, you know what is group, but one extra thing, that for every two elements in the group, A star B equal to B star A, that means it is a commutative property. Very easy, correct? In a group, if commutative property holds good, that for every two elements, then that is called abelian group. Remember it. Okay, in the GATE exam, they will give you one structure and they ask whether it is abelian group or not. Easily we can answer. We will see such examples.